Campi Flegrei shook harder than it ever has in the modern instrumental record, but the most important signal may not be the earthquake itself. On July 31, 2026, a magnitude 4.7 event struck beneath the caldera west of Naples. It opened a swarm that produced hundreds of earthquakes across the Solfatara, Pisciarelli, Pozzuoli, and nearby coastal sector. The latest weekly bulletin counted 456 events provisionally during the reporting period, with 245 already located, and 217 assigned to the swarm that began with the main shock. The ground was already rising, the hydrothermal system was already warming, carbon dioxide emissions were already following a long-term upward trend. Those facts make a dramatic title easy to write. Magmatic fluids are rising beneath Italy's supervolcano, and scientists are watching closely. The title is supportable, but only if one distinction stays visible from the opening sentence to the final image. Magmatic fluids are not the same thing as rising magma. A magma body deep below Campi Flegrei can release water, carbon dioxide, sulfur-bearing gases, and other volatile components as pressure and temperature change. Those fluids can move upward through fractures, mix with groundwater, heat the shallow hydrothermal system, pressurize porous rock, and help trigger earthquakes without a column of molten rock moving toward the surface. That is the central mechanism in the current unrest. It is also the reason the latest data can be serious without being an eruption countdown. The August 4th bulletin from the INGV Vesuvius Observatory reported an average uplift rate of about 10 millimeters per month since early February. At the Rione Terra monitoring station, total uplift since January 2025 had reached roughly 30 centimeters. Geochemical instruments continued to show the multi-year pattern of heating, pressurization, and increased fluid discharge from the hydrothermal system. Yet the same bulletin stated that the monitoring picture did not contain elements suggesting a significant short-term evolution. That sentence is not a dismissal. It means the volcano is restless, monitored at elevated alert, and physically changing, but the available observations do not show the coordinated escalation normally required to say an eruption is approaching. For clear Earth hazard documentaries that follow the mechanism beneath the headline, subscribe and stay with us. The real mystery at Campi Flegrei is not whether fluids are moving. Multiple lines of evidence say they are. The harder question is what those fluids are doing to the rock between the deep magmatic system and the streets above it. Campi Flegrei is not one volcanic cone. It is a broad caldera filled with towns, ports, roads, neighborhoods, ancient craters, fumaroles, and the western districts of Naples. Its unrest is expressed through bradycism, the alternating rise and fall of the ground produced by pressure changes beneath the caldera. Since 2005, the dominant motion has been upward. The center of deformation lies around Pozzuoli and the Solfatara Pisciarelli sector, where the crust is hot, fractured, and saturated with fluids. Most earthquakes occur within the upper few kilometers because deeper rock is warm enough to deform more plastically rather than breaking in brittle failure. Imagine a layered pressure system. At depth, magma releases volatile, rich fluids. Above it, fractured rock and faults provide pathways. Closer to the surface, a hydrothermal reservoir contains hot water, steam, carbon dioxide, and altered minerals beneath rock that can partly trap pressure changes beneath the caldera. Some fluid escapes through fumaroles and diffuse soil emissions. Some remain stored. When the balance changes, the ground rises and faults slip. The July 31st earthquake did not create this system. It occurred inside a system already being loaded by long-term deformation and fluid circulation. The word supervolcano needs its own boundary. Campi Flegrei produced enormous caldera-forming eruptions in the distant past, but the modern hazard is not limited to another event of that scale. Civil protection planning uses a range of possible eruptions, and the most probable future eruption based on the past record is smaller than the ancient caldera-forming events. Even a comparatively modest explosive eruption would be dangerous because vents can open in different parts of the caldera, and because pyroclastic flows, ash, and local hydrothermal explosions would occur inside a densely urbanized region. The famous label describes geological capability. It does not identify the size of the next event. That difference allows the story to stay urgent without claiming that Campi Flegrei is preparing a civilization-ending eruption. The current observations concern unrest inside an active caldera, not the reawakening of one single giant chamber. That is why scientists compare seismicity with gas, temperature, deformation, gravity, electrical conductivity, and the geometry of the faults. A single earthquake shows that rock broke. A combined pattern can show what is driving the stress and whether the plumbing system is changing. The main shock was located only a few kilometers below the surface, which helps explain why residents felt it so strongly. Yet the deformation record did not show a significant acceleration before the event. That combination supports a mechanical interpretation in which accumulated stress and fluid pressure finally broke a shallow fault, rather than a sudden new magma intrusion announcing itself through a rapidly changing uplift pattern. The earthquake still matters, but its meaning comes from the network around it, not from magnitude alone. The latest swarm, therefore, matters for two separate reasons. First, the 4.7 event was the largest energy earthquake recorded at Campi Flegrei since modern instruments became available. That raises the immediate seismic concern for buildings and residents already exposed to repeated shallow shaking. Second, the swarm occurred inside a caldera, where new research has mapped possible routes linking deep pressure sources to the shallow hydrothermal zone. The earthquake is the visible event. The moving fluid is the hidden carrier, and the dangerous misunderstanding is to assume that evidence for one automatically proves the other is about to erupt. The strongest evidence for rising fluids comes from the way different instruments see the same underground system. A 2025 study used improved earthquake detection and seismic imaging to separate shallow and deep activity beneath Campi Flegrei. The shallow earthquakes traced pathways consistent with fluids moving upward through the brittle crust. Deeper earthquakes formed an almost continuous ring above the inferred magmatic source, suggesting that stresses generated at depth were being transferred into the surrounding rock. The result did not show a magma column climbing toward Pozzuoli. It showed a connected pressure system. Another 2025 investigation produced a high-resolution three-dimensional image of the central caldera. The researchers identified a gas-rich reservoir below roughly 2 kilometers, a deformed caprock between about 1 and 2 kilometers, and deeper basement rock below approximately 3.5 kilometers. Those layers matter because they control where pressure can accumulate and where fractures can open. A gas-rich reservoir behaves differently from a chamber filled entirely with liquid magma. Gas is compressible. It can store pressure, expand as conditions change, and move through permeable zones much faster than molten rock. The overlying caprock is not a perfect lid. Fluid movement also changes the rock chemically. Hot acidic water can dissolve some minerals and precipitate others, weakening one zone while sealing another. Clay-rich alteration can reduce friction and strength, but mineral deposition can temporarily close a fracture until pressure reopens it. This means permeability is not a fixed property on a map. It evolves with every pulse of heat, gas, water, and deformation. A pathway that released pressure last year may become blocked this year. Another fault may take over. Surface vents can migrate or change output even though the deep source remains broadly stable. That shifting network helps explain why the unrest arrives in episodes rather than rising smoothly like pressure in a simple tank. It is fractured, heated, chemically altered, and repeatedly stressed by uplift and earthquakes. Some fractures seal as minerals precipitate, others reopen when pressure rises. The plumbing system can therefore switch pathways without changing its overall source. This is one reason surface fumaroles can evolve while the deeper magma remains at roughly the same depth. At Pisciarelli, instruments measure carbon dioxide flux, fumarole temperatures, and changes in the hot mud pool. At Solfatara, the BG fumarole has shown a long-term temperature increase, reaching an average near 173 degrees Celsius in the latest reporting week. The temperature is not the temperature of magma, it is the measured temperature of gas emerging through the hydrothermal system. That distinction prevents a common conversion error. A hotter fumarole does not mean molten rock has reached the surface. It means more heat, fluid, or both are being transferred through the shallow system. The same caution applies to carbon dioxide. Much of the carbon dioxide emitted at Campi Flegrei has a deep magmatic origin, but the route between source and atmosphere is complicated. Gas can dissolve in water, react with rock, form minerals, separate into different phases, and mix with shallow groundwater before reaching a sensor. A change at one station can also reflect rain, pressure, local fractures, or changes in the vent itself. Scientists therefore focus on long-term patterns and agreement among multiple sites rather than one isolated spike. The August bulletin reported that one Pisciarelli station showed no significant weekly change and remained within the established multi-year upward trend. Another station recorded a renewed rise in carbon dioxide flux during recent months after a period of slight decline. That is not the signature of a single new pulse racing upward on one day. It is the signature of a system whose fluid output has been changing over years. Research on the caldera's weak layers helps explain where that pressure may collect. A 2025 study identified an important transition around 2.5 to 2.7 kilometers deep. Below that boundary, the crust appeared more porous and permeable than expected, creating conditions where magmatic fluids can accumulate. As the fluid volume and pressure increase, the surrounding rock deforms. Faults respond. The shallow crust breaks in swarms. The same weak layer may also influence how a future magma intrusion would move, but that is a conditional statement. A structure capable of guiding magma someday is not proof that magma is moving through it now. Deeper imaging adds another scale to the picture. Magnetotelluric surveys have mapped a multi-level magmatic architecture down to about 20 kilometers. Receiver function research published in 2026 identified a shallow, low-velocity zone near 10 kilometers and a much deeper, partially molten region beginning around 25 kilometers. Those zones are reservoirs and transfer regions in a crustal system, not one giant open chamber. Campi Flegrei is better pictured as a network of storage zones, fractures, reactive fluids, and changing permeability extending from the upper mantle to the surface. Pressure can move through that network faster than magma. Gas can rise while melt remains stored. Heat can reach the hydrothermal system without an intrusion entering the final kilometers beneath the caldera. Very long-period seismic signals provide another clue. Researchers have interpreted some of these signals as resonance inside fluid-filled fractures connecting the deeper deformation source with fumarolic areas near the surface. A fracture filled with compressible fluid can vibrate after a pressure disturbance, much like air and liquid oscillating inside a complex pipe. The signal reveals a moving or resonating fluid system, but it does not identify one inevitable outcome. The same pathway can release pressure safely through degassing, remain pressurized, trigger an earthquake, or reorganize when mineral deposits alter its permeability. That uncertainty is the scientific reason for close monitoring. The instruments are not waiting for one magical precursor. They are watching whether the layers begin changing together. Campi Flegrei has produced both outcomes that make the current unrest difficult to interpret. In 1538, unrest ended in an eruption. During the years before Monte Nuovo formed, the ground near Pozzuoli rose dramatically. Civil protection summaries describe uplift reaching about 19 meters in 2 years before the eruption. Earthquakes, shoreline changes, and intense deformation accelerated until magma reached the surface west of Pozzuoli. The eruption began in late September and built a new volcanic cone within days. That history proves that bradyseism can be part of an eruptive sequence. It does not make every period of uplift a replay of 1538. The current uplift is measured in centimeters per year rather than many meters over 2 years. The modern pattern has also persisted through repeated accelerations and slowdowns since 2005. The source geometry, gas system, fault network, and urban landscape are different from the 16th century sequence. Most importantly, the final transition before an eruption would require more than a continuation of the same long-term trend. Scientists would look for evidence that magma itself was moving into shallower levels, changing deformation geometry, gas composition, earthquake depth, heat output, and the frequency or character of seismic signals. Campi Flegrei also provides the opposite historical lesson. During the 1982 to 1984 crisis, the ground rose rapidly. Earthquakes repeatedly shook Pozzuoli, buildings were damaged, and many residents were displaced. The unrest was severe enough to transform daily life and force major emergency decisions. No eruption followed. The system eventually entered a long period of subsidence before uplift resumed in 2005. That episode proves that a caldera can release enormous pressure through deformation, fracturing, and fluid movement without magma reaching the surface. The two histories create a difficult monitoring problem. The comparison also changes how scientists interpret records. A new maximum earthquake can be important for seismic hazard without being a new volcanic regime. Faster uplift can increase concern without identifying the material causing it. A gas change can indicate deeper input while still leaving the magma far below the level required for eruption. The evidence becomes strongest when the timing aligns. If deeper earthquakes begin first, then deformation changes shape, then hotter magmatic gases appear across several stations. The sequence would be more difficult to explain through shallow hydrothermal pressure alone. If one variable changes and the others remain stable, multiple interpretations remain open. Campi Flegrei has repeatedly taught scientists that magnitude is not the same as meaning. The system can generate intense social disruption during non-eruptive unrest, while the final approach to a small eruption may involve a pattern that is geographically focused and faster than the decades-long background crisis. 1538 says uplift and earthquakes cannot be converted into a countdown. The current crisis sits between those lessons. The July 31, 2026 earthquake made the seismic risk immediate. Shallow events can damage vulnerable buildings even when they do not indicate an eruption. The swarm also produced small discontinuities in several GNSS records near the center of deformation, which INGV was still analyzing to determine whether they represented real cosseismic movement, station effects, or another source. That investigation is important because an earthquake can change local permeability. A fault that slips may open a path for fluid, close another path through compaction, or redistribute stress onto neighboring fractures. After a large swarm, gas and deformation data can show whether the system simply relaxed or reorganized. This is where the phrase magmatic fluids are rising needs its most careful boundary. The fluids are part of an active upward transport process documented by geochemistry, seismic imaging, and physical models. But the rate, exact path, and quantity cannot be read directly from one surface measurement. The underground system is not transparent. Scientists infer it by solving several inverse problems. They record an effect at the surface. then test which underground structures could have produced it. A low seismic velocity may indicate hot rock, fluid, partial melt, cracks, or a combination of them. High electrical conductivity may indicate saline fluid, melt, clay, or interconnected pore space. Ground uplift may come from pressure in a deep source, pressure in a shallow hydrothermal reservoir, elastic response of surrounding rock, or several sources acting together. No single instrument can uniquely identify every component. Agreement among independent methods makes the interpretation stronger. That is why the recent studies matter. Seismic imaging, magnetotellurics, geodesy, gas chemistry, and thermofluid models are increasingly describing the same broad architecture. Deep magma releases fluids. Those fluids migrate into a shallower gas-rich and hydrothermal system. Pressure accumulates beneath altered and fractured rock, and the crust responds through uplift and earthquakes. This architecture explains the unrest without requiring an imminent intrusion. It also reveals another danger that is separate from a magmatic eruption. The Solfatara-Pisciarelli area contains hot, pressurized fluids close to the surface. Under certain conditions, abrupt decompression or interaction between hot fluids and external water can produce hydrothermal explosions. Such events are different from magma-driven eruptions. They can be smaller and more localized, but they are capable of ejecting hot water, steam, mud, and rock fragments near the vent area. Research published in 2026 on the Pisciarelli field reconstructed faults and fluid pathways that control gas accumulation and intense degassing. The work was designed partly to improve understanding of sudden hydrothermal explosive potential under current conditions. That does not mean an explosion is forecast. It means the shallow system carries its own hazard even while the deeper magmatic question remains unresolved. The midpoint reframe is therefore not that scientists discovered an eruption moving upward. They discovered a more connected system than the surface suggests. Deep magma, rising volatile-rich fluids, a pressurized hydrothermal reservoir, shallow faults, and densely populated ground are linked physically, but the links can transmit pressure without transmitting magma all the way to the surface. The same connection that creates the warning also creates the uncertainty. What scientists watch next is whether the current pattern stays within its established range or begins changing in coordinated ways. The first variable is seismic depth and migration. Most current earthquakes occur within the brittle upper crust. If earthquake activity began moving systematically upward from a deeper source, or if new seismic signals indicated magma fracturing rock at depth, the interpretation could change. The second variable is deformation geometry. A steady uplift rate centered on the established zone can continue during hydrothermal pressurization. A new center of uplift, rapid acceleration, or a shape inconsistent with the existing source could indicate a different process. The latest bulletin showed about 10 millimeters per month of average uplift since early February and no significant change before the July 31st earthquake. The small discontinuities recorded during the event were still under review. The third variable is gas chemistry. Carbon dioxide alone is not enough. Scientists compare ratios among carbon dioxide, methane, helium, sulfur species, water vapor, and other components because different mixtures can reveal temperature, pressure, water rock reactions, and the depth of degassing. A strong sustained shift toward a hotter magmatic signature across multiple stations would carry more weight than one local fluctuation. The fourth variable is heat. The BG fumarole near Solfatara averaged about 173 degrees Celsius during the latest week, continuing the long-term rise. Scientists compare that surface measurement with equilibrium temperatures inferred from gas chemistry and with changes in diffuse heat and carbon dioxide output. The fifth variable is connectivity. Very long-period signals, changes in seismic velocity, ground strain, and gas pulses can reveal whether fractures are opening or whether pressure is moving between reservoirs. A more efficient connection can have opposite effects. It may allow gas to escape and reduce pressure in one zone, or it may feed a shallow reservoir faster than that reservoir can discharge. Monitoring has to determine which process dominates. This is why Campi Flegrei remains at yellow alert and in an enhanced attention phase. The operational phases are designed around that evidence ladder. Attention strengthens surveillance and planning. Pre-alarm would begin preparatory actions and movement of people who require more time, such as patients in hospitals and residents of institutions. Alarm would activate the compulsory removal of the red zone population, with the national plan estimating up to 72 hours for the full operation. Those phases are not triggered by a viral video, a single magnitude, or one research paper. They depend on an integrated assessment by monitoring institutions, civil protection, and the Major Risks Commission. The system can still make cautious decisions under uncertainty, but the decision must be connected to observed changes rather than the emotional force of the word supervolcano. Yellow does not mean an eruption is imminent. It means the volcano is above normal background conditions, monitoring and planning are intensified, and authorities are prepared to move through additional operational phases if the evidence changes. About 500,000 people live inside the official red zone. That number describes the population covered by the volcanic emergency plan, not the number currently being evacuated or the number facing immediate danger from the latest swarm. Preventive removal of the entire red zone population is tied to the alarm phase, not to every earthquake or gas increase. At the current level, the most immediate hazard experienced by residents is repeated shallow seismicity and its effects on vulnerable buildings, infrastructure, stress, and daily life. The eruption hazard remains real because Campi Flegrei is an active caldera with a deep magmatic system and a history of explosive activity. The emergency plan exists because pyroclastic flows would move too quickly for ordinary sheltering to protect people inside the red zone. Both statements can be true at once. There is no current order to evacuate the red zone. There is no scientific basis for saying the caldera is safe forever. Public communication fails when it collapses those two timescales. A headline can turn magmatic gas into magma into an eruption, and an eruption hazard into a claim that disaster is days away. The scientific chain does not work that way because the correct sequence is conditional. Deep magma releases fluids that move upward and interact with groundwater and rock, while pressure contributes to uplift, heating, degassing, and fault slip. Those processes can continue for years without eruption, or they can become part of an eruptive transition if magma begins migrating into shallower levels. The purpose of monitoring is to detect that transition before the final stage. The latest record earthquake makes the system more important to watch, but it does not erase the current official conclusion. INNGV reported no elements suggesting a significant short-term evolution based on the available monitoring picture through August 2nd. That conclusion has an expiration date. Every new swarm, gas sample, GNSS solution, satellite image, and temperature record can strengthen it or force it to change. The most responsible production language must therefore be tied to the August 4th bulletin. If the next bulletin reports a new uplift rate, a changed gas signature, deeper seismic migration, or a revised alert level, the title and opening must be updated together. For residents and visitors, the practical distinction is between information and instruction. A weekly scientific bulletin explains what instruments are seeing. Civil protection alerts and local emergency messages tell people when protective action changes. Routine unrest should not be ignored, but it should not be turned into a fabricated alarm. Picture the Solfatara crater after sunset, with no lava glowing beneath the city. Steam and gas rise from vents that have existed for generations. Beneath them, hot fluids move through fractures too small to see, carrying heat and pressure from a much deeper volcanic system. A few kilometers away, GNSS antennas measure millimeters of motion. Seismometers wait for the next brittle break. Gas instruments sample carbon dioxide and temperature minute by minute. The surface appears quiet between earthquakes. The plumbing system is not still. That is why scientists are watching closely. Not because an eruption has been predicted, but because the rising fluids are continuously testing the rock that stands between deep magma and one of Europe's most densely populated volcanic landscapes.